Hello, good afternoon, people. So you are welcome once again for today's session. We are going to continue on from where we started on Thursday. Thursday, we introduced the course and we try to do one or two things with it. The basic information that you need to get with ASPEN Plus and how you can do your simulation, how to enter components, how to set property method, and many other things were done. And we did one simple simulation so that you can know how you will be able to put a stream on a flow sheet, connect them, reconnect them, and many other things that we did. So I admonish all of us to take it serious as we continue. This boot camp covers the following outline. We have already started with the introduction and general overview. So today what we are going to do is we are going to do fluid handling equipment. So the example or the case study that we are going to take to learn today will be based on fluid handling equipment. So we are going to do that of pumps, pipeline, valves, and maybe compressors. So I admonish you that you stay keen to whatever we are going to do so that at the end you will get something from this. Once again, I want to give thanks to Chisa for giving us this opportunity. So before we start, I want to tell all of us if you haven't launched your Aspen Plus, I want you to launch it, and get to this session, the property environment section, as we begin to move. So today, the fluid handling equipment, we are going to use a case study by pumping, transporting water from one tank to the other. Thus, we have a district and we are transferring it. So I will begin to read it as you can see. Please, can you see the problem?
Yes.
Okay,
Yes, we can see.
all right. So the problem says it is desired to transport water from tank A in the district capital to tank B in a village that is 2 kilometers apart. Two pipes, different kinds of valves, and a pump is installed to achieve this fluid transport. Tank A exists at a pressure of 2 atm, which where it surfaces to push the water until the entrance of installed pump, installed at the midpoint between the two tanks. Water will continue its journey to tank B by virtue of the pump work. The following figures, the table shows specification entered for inlet stream and all blocks starting from stream 0 to stream 9, that's to tank B. So the material that we are going to use, the components will be water. We are going to transport water from one place to the other. And the mass flow rate of the water that will be transported will be 10,000 kilogram per hour. In thermodynamic condition of the water is 2 atm and the temperature is 25 degrees Celsius. This table will be the specification for the types of valve that we are going to use. So you can see we have butterfly, ball, and globe valve here. And the valve operation spec is going to be a rating valve based on the opening. And we are going to check in choke flow and cavitation index so that at the end we are going to see if there will be even cavitation within the valve as the fluid continue to flow through it. And the pump specification, we are going to discharge the pump at a pressure of 3 bar, and the pipe specification will be a screwed one, and the type of fittings that will be within the pipe will be gate valves, butterfly, large 90 degrees elbow, and straight T. And we are going to use a property method called Steam NBS. Steam NBS. The reason why we are choosing this Steam NBS, let me explain this before we go to the main flow diagram, is that per research, we have seen that Steam table by NBS or NRC, that's National Research Council, give proper estimate of thermodynamic properties for water. So it is desired that we use NBS other than the normal AMSC, American Standard of Mechanical Engineers steam table. So that's what we are going to do. So this is a pure chemical engineering problem in which we have water. For example, those in second year, maybe you have been to a field trip that you have gone to Barikese Waterworks. So they have a tank there that stores water temporary before we push it to different towns. So that will be this tank, tank A, and we have a valve installed so that it can regulate the flow of the water so that it will not be that it is moving. So we will open this valve at any time that we need, and it will enter this pipeline that will transport the water from the waterworks down up to where the pressure of the water in the tank will decrease so that it cannot flow by itself. Then we apply mechanical energy to it by installing a pump to move the water up to the different pipeline. Then it will be into the tank B so that they can use it for what to be useful. So I admonish that we all join hands as we continue to move. Well, this is our problem for today. We are going to move straight to the ASPEN Plus software and try to install it. So our chemical that component that we are using is water, and the mass flow rate uh, is 10,000 kilogram per hour, and the thermodynamic condition is 2 atm, and temperature is 25 degrees Celsius. So before I switch my own, I'll give you about 3 minutes so that you do it yourself since we did it last time. Then we will take it from there. So I want you to launch your Aspen Plus like this. If you haven't started, you can go here. So you launch it like this. You can select blank simulation, or you can select chemical properties and select chemicals with metric units. Chemicals with metric units and create it like this and create. So you can do that as I have done up to this part, or begin to do that and select the property method to be Steam NBS. If you check Steam NBS and it's not there at the commons, select all and find a Steam NBS. So all the best, do that and let's continue. Please, when you are done with that, you can give me a thumbs up so that we can continue. Okay, Jeffrey, the chemical components is just water. We are pumping water from one area to the other. So it's water. Okay, so I take it that um, we have been able to enter a chemical component. So I'll enter my own water, just as we said. You can go to find, or you can enter the alias here. So we know that water is H2O. I enter H2O and you see water is conventional and it will be liquid. So I name it as water as my ID. Now I will move to methods. I'll move to methods, and in my methods I'll look for Steam NBS. So Steam NBS. So one way that you can search for the methods, you can choose not to open everything and search for it. You can just start typing what you need. So Steam. So you see that Steam NBS is here. When you start typing ST, it will come like that. So this is Steam NBS. Alright, so this is my property method. I go to next, then I run it. Okay, as I wait. Okay, now my resources available table has been generated and it is water. So we can move to our simulation window and continue with the work. So switch from property environment to simulation window by just clicking on simulation. Okay, so now there's the work that we are going to do. So we are supposed to choose a model to represent its tank A, and we are supposed to add the streams to it and move. One of the cautions that you have to know when you are using ASPEN Plus is that it's a sequential uh, simulation tool. That means if you come to this flow diagram, when you are finished inputting everything for this, ASPEN will start with the first unit. It will process the first unit before it takes that results to the valve and works from here up to time B. So it's better you build your flow sheet one by one. So you start from zero, you build it, you run it to see that your results are available, then you add other units, then you move from there. So that's what we are going to do. And at the end, we discuss the results that we get. So those who know it, as we learned, just add the material stream. Today we are adding material stream first. So you click anywhere and draw it to where you need it for some purpose, then click on it. Now my own is telling me to give a name to it, and I'll name it just as we name it on the main flow sheet as zero. Maybe somebody is here that your stream doesn't give you the option to name it, and that is because that it has been set like that. So if you want to change it and you want to give a name to it, you don't want the Aspen to give it a default name like 1 or S1. What you do is you come to file, then you move to options. So in options, come to flow sheet. Or in flow sheet, scroll down, okay, and get to this part, stream and unit operation labels. So you will see that we have automatically assigned block name with prefix. Do you have a question? Okay. So we have automatically assigned block name with prefix. So if I check in this, it will ask me the block name that I want it to be. So if I leave it as B, as this, so I'm going to leave it as B. When I bring the block, it will just name it as B1, just like that. B1 just like that. And you have seen that the stream name, I have deactivated it. So I'm going to check it in. So that one also is going to be S. So it will be S1. Then we will rename it back to our 1 and 0. So if you don't want yours to be automatically generated, you can check them off. Check them in so that it will be off. Okay, apply. Let's move on. So now I'm supposed to bring a tank to name it tank 1. So tank can be found at where we have the mixes. So check mixer, mixer slash splitters. Click on the drop down. So you see that we have a lot of models for it. So pick the tank. It is indicated as tank. So you click on tank. Then the insertion mode will change. So just put it on it. And now you can see what I was talking about. This time around, I'm not supposed to give a name to my block, but rather the block name has already been given. So I have to deactivate the symbol, the insertion mode. We will come here, cancel the insert mode. Then I want to rename this unit, this block as tank A. So what you do is you select the name, you double click on the naming B1, It will highlight it. Then you can delete it with backspace and give it a name that you want. So the name that I'm going to give is tank dash A. Remember, it can take up to 8 characters. 8 characters. So that's tank A. So I bring tank A down here. Then I'll bring the new stream. That will be the outlet of this stream. So this one too, I click it. Then I'll just click on anywhere and send it forward. So now you can see what I was talking about. Now it is stream S2. Since we have already inputted the first one, it's S2, it will give it a name. So I need to change this name to 1. This one also, what you do is you double click naming, then you click on 1. So when you click on 1, then it will rename it for you. If you don't want it like this, you go back to file, options, flow sheets, and you come to stream and unit operation labels and check the automatic off. So now I've checked it off so that you can know how to do it. All right. So now I have to connect these streams to the unit so that I'll get a flow diagram. So what you do is last on Thursday I showed you that if you want to reconnect a stream, just select it like this and right click. When you right click, then you go to reconnect. Because the stream is entering the unit, you go to reconnect to destination. So you click on destination and it will change and you hit it to the red. I told you that the red means it is required for it to be filled before you can move on. That's one way. You can also, this arrow, you can double click on it also and it will um, tell it to connect to destination. So I will just double click on the arrow like that and you see that it has changed. Then you take it to the red button. Now you can see that it has been connected. The same thing. So I'm not going to do reconnect, right click. I'm just going to hit on this one backwards. Then I'll select it just like that. So once I'm done with the flow sheet, the next thing that I have to do is to specify the process conditions for material stream. So you don't know where to go next, use the ASPEN next tool. So you come to home, then you click on next. Click on next, and this next will bring you here. So here, now you have to fill this place. And last week we showed how we fill it. So this one too, I'll give you 1 minute so that you fill it. The temperature is 25 degrees Celsius. The pressure is 2 atm. Not bad, 2 atm. And the total flow rate is 10,000 kilogram per hour. So use this opportunity within the next 60 seconds and do it. Okay, so now the temperature is 25 degrees Celsius. The pressure is 2 atm. So you can change the name here. So you can change it here. You come here. All the units for pressure is here. So you go to atm. So this is atm. Atmospheric unit. It's not gauge. So atm. Now our flow basis is mass. So I'll select mass. On Thursday, when we were doing it, when we select mass, you type the total flow rate here, then you come and use composition here. That's one way. You can choose to type the total here and come and type the composition, the mole fraction or mass fraction at the composition section. Or because it is one, or if you know the flow rate, you can change the flow to mass flow and set the unit to appropriate unit and also type the amount that is needed here, amount given here. So this is 10,000 You can do it like this, or you can go by how we did it. You type the total here, then you come and check the composition to be 1. So now that we are finished with this, you can see that everything is complete. You can see that this is blue. So when the sky is blue, it means you are true to go. That's been fully specified. Then you can run. So you can use next. If you don't know what you have to do next, use next, go to next, and it will tell you that everything is complete. So run the simulation now. Okay, we run it, wait for the results. Okay, so now you can see that the results is complete. The results is complete, and it's just a tank. So what is inside will be the same thing that's coming outside. So I want my flow diagram to be nice. So just as I showed you, use Control A to select all, come to modify, and align the streams. So I'll align my own, and you'll see that now it is straightforward. That's been straightened. Okay. So if I want to know the mass flow rate in and out, I'll just check in mass here, and you see that it's still the same. It's still the same. So this is the first session. So now that we have finished with the first session, let's move on to the problem. So now we are supposed to put a valve here that will be a control. Should the water go into the pipeline to transport it up to where the pump is? So we are going to do that. So we are going to install a valve. Or to install a valve, look for pressure changes at the model palette. So look for pressure changes. So I will select pressure changes. And you see that we have pump here, we have compressor, multi-compressor, we have a valve, we have a pipe, and we have a pipeline. So the difference between the pipe and the pipeline is that a pipe have a single diameter, but the pipeline have different diameters. So you can get a pipeline that is moving from maybe engineering or the auditorium to chemistry block. So the diameter for the pipe from engineering auditorium to Banfo Kwachi building may be 5 inches, and from there to College of Science will be 2 meters. So that will be a pipeline. But the pipe have only one diameter. Okay. So now we have to put the valve to the flow sheet. So just select the valve. If you don't like this icon, you can click down, you find different ones that you like, then you pick. So I will check in this one and come to the flow sheet and select it anywhere. So now I'm supposed to give a name to it, and now I'm going to give it v-1. Okay, it was valve 1, so valve-1. Let me make it a bit different, v-1. Okay. So if I want to enlarge it, you can select it just as I showed you last week and enlarge it. So I bring the labeling down. Now I have to put outlet stream to it. Always make sure that your stream is in and out. It has been connected. So I select it and I'll bring the outlet. I can select it and bring it. So I'll put it here, check in the product and send it out. So I'll give it, this stream is called stream 2. So now what we have to do is to reconnect the stream 1 to the valve. So you double click here, then you join it to the valve. Now let's move on. Now that we have checked here, you can see that the block is having the half red circle. That means the record input is not complete. So let's go to home, or you can come to the title bar. You see the next two there and click on next. It will take you to what you have to specify. Now it has brought us to the interface of how we have to specify the valve. So the V1. So this V1, when we come to the valve session, in the problem said we should make the calculation option a rating one. So rating in a sense of it will be rated according to the opening. That's how we are going to check it. We are going to specify it. We are going to specify it. And the V1 is a butterfly valve. So now you come to the window and you check in adiabatic flash for outlet pressure. So for this one, you are supposed to just give the outlet pressure that you need. But this time around, we don't need that. We don't want to impose a pressure that an outlet pressure on the water so that from 2 atm it will just come to 1 bar. No, we want to give it a rating opening so that we will see how much pressure drop can occur as the water flow through the valve. So we are going to check in calculate outlet pressure for specified valve into bracket rating according to the rating, and the rating is according to the opening of the valve, the opening of the valve. So here we can see that we were given in the problem that the valve operation spec is 50% opening. So we will come to the stream and type 50 here, not 0.5, 50, because percentage symbol is there, 50. So now when we check this, you see that the operation side has been specified, so it has ticked blue. And we have to move on to valve parameters before we can finish with this. So now, let me talk about the flash option. So there are a lot as we continue with the bootcamp exercise. I will show you a lot. Now we are dealing with water alone. This flash option here determine the phases that we are working with. So now we are working with liquid water. We can choose to let the phases be vapor dash liquid. That means the phases that's happening within our work can be vapor phase or liquid phase, and it will just work perfectly. Or better still, we can still change it to liquid only. That means only liquid phase exists. Okay, so you can change yours to liquid only, or you can leave it as vapor liquid and it will not cause any problem. But if you check it to vapor, it will not work for you because the water was specified as a conventional, and the conventional water that we know and the temperature that we specified was 25, and water at 25 degrees Celsius is not uh, vapor phase. So you can leave it as liquid only or vapor liquid. So now that this is okay, let's move to valve parameters. So now with the parameters, everything has been stated in the problem. It said the valve type for the first one is a butterfly valve. It's a butterfly valve. And the manufacturer is the default that ASPEN has been given, Nellis. Then the style or series is going to be 300 ANSI. Then the size, that's when we talk about the size of it, what we are talking about is diameter. So the size is 3 inches. So once you are done with this, you see that the opening, the valve parameter table will be generated for you like this here. So if you want to understand this table, the CV, the FL, and the ST, ASPEN has a help tool here that contains the note of everything that we are doing. So the simple way to direct us straightforward to C, you can just select the CV like this and hit on function key and F1. So when you hit on it like this, a new window will open. Just as it is opening on my uh, screen. Then it will bring you here. Then it will tell you we have valve input valve parameter sheet. So you will see that the XT is ratio factor, pressure drop ratio factor, and FL is pressure recovery factor. So you can read about these things here. So anything that you don't understand, you can just just select it and click on function key and F1. It will send you to the main node. So this is the node, every node that you need for ASPEN it has been embedded in it. You can go there and read. Okay, so now that we have specified the flow rate as that, you can see that at 10, there is the CV, XT, and FL that's given. And we selected our 10 to be 50. So at 50, this is what we are is going to work. So this goes beyond this um, bootcamp exercise, this webinar. So just leave it for you to read it yourself to get understanding. So now we go to calculation options. So this is the thing that you want asking to calculate it for you. If you want choke, you want to see choke, you want to see cavitation index, if cavitation will occur within the valve, then you can check it. So since we want to see what will happen in the valve as the water flow, we will check in the cavitation as well. Then after that, we go to next and okay to run it. Now my results is available without warnings and errors, or we can move. Okay, Felix, Jeffrey.
The valve parameters.
Okay,
Yeah, I want to see the, like, I didn't get there, so I don't know how you pass
all
there.
all right.
Yeah. So if you can go back there. Yeah.
Let me go back. All right. So this is the valve parameters. So with the valve parameters from our problem, we are using a butterfly valve, and this is the star ANSI plus 300. I think you can read about it more. And we have
Okay,
the
okay. I have the same thing. This one. Yes.
right. So so what you have to expect is that since we have installed a valve, there is going to be a drop in the pressure that's coming. So we will view the total results after everything, but yet still we can check in the pressure to see what is happening. It's still true here because there is no decimal places for it to show. So if you want to change how this appear, you can. All right, let me leave that for now. We'll talk about that later in the course. So now we want to see the results here. What is happening? We have installed a valve and we expect that something should drop or something. So you can come to stream, come to all boundaries or all for your results. When you come here for your result from 0, you see that the phase is liquid phase, even though I didn't leave it as liquid only, but ASPEN detected water at that temperature to be liquid phase. And you can see that now the pressure, let me leave the pressure as ATM. So if you change the pressure to ATM, you can see that the pressure exiting the valve has been decreased a bit. So you can see that there has been some pressure drop in the valve, and I think you understand that when you install a valve, uh, the piping system, there's supposed to be a drop. There's supposed to be a drop. Okay. So now that we are done with this, okay. So now we are supposed to go to our main problem and see what we have to do next. So when you come here, after the valve that we have installed, that's going to control the flow into the main pipeline. The main pipeline, we have to install the pipe 1 and move. So now we go to the environment again, but before we do that, I'll give you time. Please save your ASPEN document at APWZ. Since I don't know who is using the original file here, but it looks like me myself, I'm using a crack file. So before it will crash for us, save it. So I'm saving it as boot um -2, and I'll put it at my ASPEN class folder. So Bootcamp is here. So let me put it here. So once I save it, you see that my title bar has been changed. Okay. So are you done? Okay. All right, Amos. Okay. Now let's move on and install the pipeline. So we are going to install this pipe. So the same way is a pressure changer. Just select the pipe and put it at the flow sheet. So I'll bring it here and name it pipe 1. Pipe 1. Pipe dash 1. And connect streams to it. Since now you know how to connect streams, just connect streams to it. So you can enlarge it. I'll connect my stream. I'll select it will be fourth stream. So one way that you can deactivate an insertion mode, that wherever it is, just right click. If you right click, it will just deactivate it. Or when you bring it, just use the escape button. So when you use the escape button as well, it will also deactivate the insert mode. So now we reconnect, double click, then connect the feed stream. Okay, so I like to align it. All right, so now I don't know what to do next. Let me bring my valve here. So what I'll do is I'll ask ASPEN next. Where should I go to take you to the next thing that you have to specify? Now, it has brought us to the specification of the pipe parameters. So now you will see that this pipe, it will ask you, what's it doing? Is it conveying solids or is a fluid flow? And we all know that we are conveying water. We are just pushing water from a district capital to a village. So it's water. And the first one is 1 kilometer. It's moving it from 1 kilometer by the power of the pressure of the fluid itself. So it's just flowing by itself before we install a pump. So now we are supposed to specify the pipe length. So that's 1 kilometer or 1,000 meters. So this is one. Then you can change the kilometers here. So you can go along and look for kilometers as this, or just as I show you, start to type km, and you see that kilometer has come. Now we are supposed to specify it. Oh, let me come to the problem. Pipe specification. Oh, then add the pipe specification. Now this is how we are going to define our pipeline. We are going to do the pipe schedules for our pipeline. That's how we are going to define it. And our nominal diameter was calculated uh, using this formula. I think those who are in final year and they are doing design, you will need to specify your pump, your pipe diameter, and you will be making using use of this formula. So we converted the mass flow rate to volumetric flow rate, just put it here, and the density of water in feet cube. So when you finish, you just put it into this formula and it will give you the diameter, the nominal diameter of the pipe based on the flow rate that we are using. So you use it to specify your pipeline. So you can see 2.3, we don't have 2.3 nominal diameter, so it's closer to 2.5. It's better we use 2.5 than we use 2.0. Right, so we are going to use a 2.5-inch nominal diameter. So you select use pipe schedule, and the material that we are using, we are going to use a stainless steel. for our work, and we are going to use 40 schedule number, and the nominal diameter we are choosing 2.5 from the calculation that I just demonstrated. So 2.5, just like that. So when you are done like this, you see that it will be specified. You can move on. But there is more that we have to add to it so that we can move. A pipeline will have some fittings. So we have to specify those fittings and move. So you come to thermal specification, and we are going to set it to adiabatic. Then we go to fittings, and for the fittings, you have two gauge valves within the pipeline, one butterfly valve within the pipeline, six 90-degree elbows, and straight tees. We are going to have 10. So in all, we are having 19 fittings within the pipeline alone. So at the end, we are going to see the pressure drop that will happen within this pipeline. So those who are in final year, when you are doing plan design, you see that after everything, you do calculation and you calculate equivalent length based on the drop that will happen, the length that the fluid needs to take to move. It will not be the 1,000 meters. It will take more than that to do that. So we are going to ASPEN is going to calculate all those things for you. Okay. So if you have been able to specify this, so let me go over again. The pipe, the first diameter up to where we have the pump, because we are using the strength or the power of the water that's coming, 2 atm. Then the pipe length is 1 kilometer. We are using pipe schedule, and the material that we are using for this is stainless steel, and we are using a schedule number of 40, and the nominal diameter, just as we calculated by the flow rate, is also 2.5 inch. And we come to the thermal specification. We are doing a diabatic operation in this pipeline. Then we move to this part. Okay, so this part we said we are going to use screwed. I remember the question said we should use screwed. Okay, so the pipe specification, okay, so it's here. All right, the pipe specification is here. The type is a screwed one. So you can see this is a screw. And we have the gauge valve to be 2, butterfly valve 190 degrees, and 6 straight teeth. So we are supposed to select a screw. So when you are done like that, you can go on to the flash. Still, it is vapor liquid, and you know that because it is liquid, it will be liquid. You can still change it to liquid, it will not do anything. But let's leave it as it is and run. Or you can run it or go to next and run. All right, so now my results is available. So I will save it because I don't know what will happen in the next second. All right, it's done so that we can move on. Please, who has a problem with the specification of the pipe? Okay. Please, who are able to specify the pipe? Please, if you have been able to specify the pipe, uh, give me a thumbs up. Okay, Amos. All right, so Vincent, I'll go over it again. So once you bring the pipe to the flow sheet like this, just double click on it. So it will bring you here. We said we are using the um, pressure of the water in the tank just to move it. Water moving at 2 atm can just be left at PB just to flow to this place, the new engineering building, without we adding any external force to it. So we will just leave that one to pass through the pipeline and move. So you will specify the pipe length. The first pipe that we are using is 2 kilometers. Then the first pipeline is 1 kilometer. Then you come to the use pipe schedule. We are using pipe schedule to specify our pipe. Then the material, we have carbon steel and stainless steel. You select stainless steel. Then the schedule number, we are using 40 schedule number. Then the nominal diameter is 2.5 inch. Leave the roughness as it is. Leave erosional velocity coefficient as it is. Pipe rise, there's no inclination in it. So that one, no pipe will not rise, it's just horizontal as it is. Horizontal. Then you come to thermal specification, you make it adiabatic. That means zero duty. You are not adding any heat to it. Alright. Then you come to fittings. So for the fittings, the connection type, you come to a screwed one. A screwed. So if you have been to the unit operation lab one before and you come to where we have the pumps, you see that we have somewhere the flanges have been welded. It has been welded, and some places it has been screwed. So we select screwed connection. Then the valve, gate valve, we see that the problem says we should use gate valve 2 to be 2, the butterfly valve 1, 90 degrees elbow to be 6, the straight teeth to be 10. Then that's all. Then you run it. Please, are you okay, Vincent? Vincent, are you okay? Okay. So now we are doing it and we are not assessing anything to see. So now that we are done with the pipeline, uh, we check in. If you check in the pressure, you will see that now it started as 2 atm, 2 bar here, 2 bar. But as it comes out to the from the pipe, you see that now the pressure has been reduced to 1. So if we want to push it to the next town, maybe now it has reached, we are pushing it from here, from we are moving water from Barakese Waterworks to this place. Now it has reached Swami roundabout, and the pressure is now 1 bar. It can't flow up to this place. It means it needs an external force, and that external force will be the pump that we are going to install to do the work for us. Okay, so now we can try to check the pipeline to see the results from the pipeline. Just click on the pipeline, right click on it and check the results to see if there is anything that's happening. So you see that the total pressure drop within the pipeline is 4.1, 1.489 bar. Then the frictional pressure drop is 1.489, and you will see that the heat duty in kilowatts is 3 times 10 to the power negative 6 kilowatts. And now you can see that the equivalent length as a result of the installed fittings is no more kilometer, 1,000 meters. So let me keep it at kilometers. It's no more 1 kilometer, but some things have been added to it because of the fittings. That's causing the drop within the pressure. So if we come to the stream, you will see that there is the inlet pressure that's coming in bar, and there is the outlet pressure. It's very low. The reason why when we check in to see it at this one is because we haven't set the number of decimal places that should be there. So it has rounded 0.5 to 1. We will do that very soon when we break for the second session before you continue. Then you can see the temperature. It has increased. The temperature has been increased and you can relate it. And we have the mixture velocity, erosional velocity. We have Reynolds number. The Reynolds number here too, you can see that the flow is turbulent. Looking at the number, the Reynolds number is turbulent. So you see that before it was there, the Reynolds number was 63,330 and now it has increased to 75. 75. Okay. So you will see as we proceed and we can see the balance, let's see. Okay, so the balance, you see that the energy balance and the mass balance, you see that the difference is zero. It's the same water that's coming out. And you can see the profile of the pipeline, So you see that there is a summary. Okay, let me select all, so that you see at 0 meters, at 100 meters, that's 0.1 meters. You see the pressure of the water that's coming in. So it flows down up to when you get before it discharge. You see that the pressure is now 0.5. That means there has been a drop in pressure as it moves through the pipeline, and you can relate the Reynolds number differences also here. Okay. So maybe you want to graphically see what is happening. You can go to custom. Look at where we have the plot. Custom. So you click on custom, then the pipe length diameter as my x-axis and the pressure in bar as my y-axis. Then I will draw the graph. Yes, so now you can see that we have a negative slope starting from 0 to 1,000. And you see that as the length increases, you see that the pressure also decreases. We are in a way of our problem. So what you do is um, right click, right click.
Yeah,
Okay.
I did, but I have a notification, a warning that sorry, due to an internal error, your plot could not be created.
All right. Which version are you using?
Version 11.
All right. I had the same problem when I was plotting the version 11, the graph with the version 11. So I think it's a technical error and it's beyond our control. So
Oh, okay.
yeah, I did same thing and I have that.
Oh, okay, okay,
All right.
okay.
So now, since you have the problem, I want you to go ahead and install the next valve in the problem. So after the pipeline, before it goes into the pump, we need to use a regulator. The regulator will be valve 2. So go to the pressure changes, and install a valve. Name it B2, B-2, and
Okay.
connect streams to it. So we connect, and that stream will be stream 5. And we double click. So after today, you should know how to use the fluid handling models here. So by the end of everything, we are going to do a plant-wide simulation. We will take a full plant, and simulate it. And when we get to some places like where we are supposed to use a pipeline, time will not be spent. So please ask all your questions here before we move on. Okay, so I connect, as you know, I connect it, I deactivate it. Now let's specify the valve. So it's the same thing as we did for the other one, the same opening, and it's a rating, and it's 50. Then you come to valve parameters. Now this type is different from what we are using. So now the V2 is a ball valve. It's a ball valve. So we are going to use a ball valve. And I think you can relate it why we are using a ball valve. So we are going to select a ball valve, and the manufacturer is James Berry. And now it is a metal seated full pot. Then the size is the same thing as that of the butterfly valve. So the beauty of ASPEN is that you are seeing them to be the same thing, but the work that they are doing is different, totally different. One is doing the work of a butterfly valve, that high pressure, and this is doing the work of a ball valve. And you see that the pressure drop recovery and everything is different in the rating table that has been generated. So once you are done with this calculation options, check in the cavitation that will be discussed later, then run. All right, so my results is available. Keep on, you can clear a window that has been opening so that you get a clean session. All right. Okay, so Jeffrey, so when you go to next and you come here, you check in rating 50, the same 50% opening. You come to here, we are using a ball valve. Everything is the same as we did for the butterfly valve with the exception of the series and the ball valve. So the ball valve is a ball valve and the style of the ball valve is a metal seated full pot. Then the size is 3 inches. So when you are done, then you run it. Now that we are done with this, we are supposed to install a pump, and we all know what a pump does. We are going to increase the mechanical energy. We are going to increase the pressure of the fluid so that it can flow to the town. When we are done, we will dress the flow sheet. So this work that we are doing, okay. So let's move on. So you come to the pressure changer session, then pick a pump. So this is pump. Bring it to the simulation. Give it a name. I'll give it pump. Okay, bring it down. Now connect the stream. So don't connect it to the blue. The blue is a dirty water. Maybe there is a dirty water and you want to take it out. No, we are pumping water. We assume that the water is clean. There is no dirty. The pump is not dirty, so that we will leach the dirty water from it. So don't connect to the blue, else when you run it will not come. So you click on the red, then this will be 6. All right, then I'm going to double click there and connect.
Clinton,
Yes, please.
please, in your pipe labeling, you have skipped 3. Can you check? It looks like there's no 3.
Z.
Your streams,
Okay,
the material stream, it looks like you have skipped 3. I
I'll
don't know.
skip 3. Okay, okay.
Yeah.
So 1, 2. Okay, thank you. This part should be 3. Then this part should be 4. Thank you very much. 4. So you can change it as well. 5. Now that we have installed the pump, one more comments. It's not asking a question and muting. Okay. Okay. So now, okay. So now let's specify the pump. So go to next if you don't know how to go, or you can double click on the pump. This pump session will be open. So go to next, and when you come to next, it will ask you the model. So the pump can be used. That icon can be used as That icon can be used as a pump or can be used as a turbine. So now we are going to use it as a pump. Then our pump specification, we are going to use a discharge pressure. So we want the discharge pressure to be 3 bar, as it was stated in the problem. And we are going to leave the efficiencies to be the same as this. So if you don't put efficiency for pump and the driver, Aspen will use its default. And the default one, Aspen have a pump efficiency to be 82% and that of driver to be 95%. So we are not going to enter any pump specification efficiency for it. We will use Aspen's own. Let's come to okay calculation option. This one we are not going to put anything there. We are not going to give the suction area. We are going to leave the faces. The faces is liquid only here. So if you check gas, pump cannot be used to move a gas. It will not go. All right. So now that we are done with this, I will run it. So you go to next and run. All right. Results is available without errors. The sky is blue. Sky is blue. So at this juncture, I'll tell you to save it as I have saved my own. Now let's move on. Now that we have installed the pump, let's go to our flow sheet and see what we have to do next. We have to install a valve before we send it to the other pipeline. So the other valve that we are going to install, I will leave you so that you install it yourself. But this time around, it is a globe valve. So you look at the problem, it's a globe valve and the type is 8 V8110 equal percent flow. So that's what we are going to use for V3. So just install V3 as I'm going to install it. Oh, V-3. Let's move. Okay. The valve is too big. So I'll connect the stream to it. And I'll connect a new one. So this one will be stream 6. Okay, I go to next. And we come to rating. The opening is 50. The valve parameters. The type is a globe. The manufacturer is still the same. The style is V810%. Then the size is 3 inches. 3 inches. Right. So when you are done with this, you can run. Okay, so we are about to finish our problem. So if you have been able to do that, I want you to go ahead and install the pipe 2, as in this pipe 2. Pipe 2. So you go ahead and install pipe 2. The pipe 2 has a specification same as that of pipe 1. So I'll give you 2 minutes to do that so that we can move. So you are in a waterworks area and you have been charged to predict what will happen. Will cavitation occur in the pipes? Will cavitation occur in the valves? Will cavitation occur in the pumps? In the pipeline when we want to transport water maybe from Barakesi to take. You can sit in your room, get correct data, model it and see so that it will mimic what we would be done originally. As I already explained that Aspen will be used to mimic a flow. Alright. Okay. So let me go ahead and install my pipe 2. So pipe, I install it. Let me bring it. Let me put it up here and give it pipe 2. Pipe dash 2. Okay, then I will double click, install. Then I'll connect my stream as stream 7. Let me bring it down as I've been doing. Okay. So I align it. Okay. Always when you are doing it, make it look a bit presentable. All right. So now I have to specify it. Same specification as the P1. So you go to next. Come here is fluid is 1 kilometer. So this time I'll type 1,000 meters. The same thing. Use pipe schedule. Using pipe schedule, stainless steel. Then thermal specification, adiabatic, fittings, the same 216. 216. Then the straight T's we have 10 or 19. The connection type is screwed. All right. Flash options, we keep it as vapor liquid. Okay. I didn't finish scheduling it. Then the diameter, as we calculated, is 2.5. Now everything is set. I will go to next and run. Okay, so results have been generated without any error. So that's it. And you can see that the pressure entered as 1 bar and the still is coming out as 3 bar, and now when it passes through the pipeline, and now it is 1 bar. So we are now going to put the water to the main storage tank at the village for the people to come for it. But before that, we have to install a regulator. So if you have been able to do up to this part, now let's install the tank. So come to mixers. No, we are supposed to put a valve there before controller. So valve there, that will be our V4, V-4, V-4. Okay, V-4. Then we connect the stream. So I'll bring the stream down. I'll put the water down. Then this is will be stream 8. Then you connect this one. Now we have to specify the valve. So it's a globe valve again. A globe valve, calculate rating 50%. Uh, so globe valve, the same manufacturer. Style is now a linear flow. We want to decrease the turbulence. A linear flow, and now it's 3 inches. It has been developed. So now we have to run. So you go to next and run it. All right, so results have been generated. You come here, you see that it's still at 1.1. That's the equivalence 1. So you check what has happened. So now that we have been able to install a valve that's going to do the regulation of flow for us, now let's get a tank. That's tank B from the problem and install it. So I want you to install the tank B. So I will tank B. You come to mixers, pick a tank, put it here. I'll put it down. Then it will be tank B dash B. Then I'll reconnect it. So I'll reconnect it. I'll just put the tank. I'll install it at the top like this. I think I've showed you how to do that. Then the water, we will let it flow from the bottom. So I'll double click as I showed you, hold and bring the stream down here. Oh, it's here. So this will be 9. So once we are done with this, you can run. Okay, now you can see that our results is available. our resource is available. So before we discuss the resource, uh, let's see the temperature changes. It's still 25. I will change it for everybody to see how the difference. So now let's try to check what is happening within the pipe. So now we started the water. Let's see the first valve. Let's see the results in the first valve. Okay, so the valve is not choked. There's no air within it. It's not choked. And the opening is 50% as we set it up. The pressure drop factor is 0.45. Piping geometry factor is 1. And the outlet temperature was this. Okay, so that's this valve. I want to see the cavitation index. So now look at this one, the pipe, the cavitation index. The cavitation index here is 0.0063. This index is in a range of 0 less than 1 less than 0 less than k less than 1. It should not be up to 1. So as this cavitation index increases, then there is a possibility that there will be cavitation in your piping system. So looking at this, there wasn't any cavitation. So this is very low. If you check that of this valve as well, oh no. All right. So if you check this one as well, you see that the cavitation index now is 0.0476. It keeps on increasing, but it's still low, so there will not be any cavitation within this valve. You will not hear any noise. Let's try and see the results of the pump. So if you look at the pump, the brake power, the fluid power, the electricity, we use electricity as the electric power. Those who have been to the pump experiment, you see that we have P electrical power. This is it. And you see pressure change that happen. And you can see net positive suction head available to be 4.80. That's the net positive suction head that was created. The available one, we don't know since we don't know the manufacturer. So what you can do to see if cavitation can occur, you are doing this one for you to compare it with real world work. You know, every pump have is NPSH required. So when you simulate it with this, you will see that no, you can tell your boss, the NPSH available that will be within our piping system is 4.8. But looking at the NPSH that's required in order for cavitation not to occur in our piping system or the work that we are going to do is 4.9. And based on that, you can look at it and you say that boss, the cavitation, in order for cavitation not to occur, the NPSH available should be greater than the required. And since it's not that, cavitation can occur. You can tell your boss like that. You can tell your boss that. So that's the NPSH available that can be calculated. And you have pump efficiency used. So you know how we calculate pump efficiency. The hydraulic power, the okay, the hydraulic power, and the input power, the mechanical power. Oh, that's the outlet pressure. Okay, so we go back to the main flow sheet. Go back to the main flow sheet to check the valve tray to see the cavitation index. Cavitation index, the same thing. Okay, so you can see that the cavitation index for valve 3, we can't see it just because when I was specifying it, I didn't check it at the calculation option. So I will go back. Let me open the main flow sheet and show. It wasn't there. So I will just double click, go back, come to calculation options and check cavitation index so that we want to see the cavitation that will occur. Then I will rerun it again to get my results. Now I'll go to V3 results. Now you can see that the cavitation index here is now 0.125. That's getting closer to 1. That is getting closer to 1. And this seems that if there is going to be any cavitation, or the valve is going to be the valve 3. So you can relate it from here. We can see the NPSH of this pump here, and you can relate it to the how the the cavitation index has increased for this one. So we can check the results for pipe 2 as well. And when you come here, you will see pipe 2, the equivalent length is the same as that of the first one. You will see that it has increased. I think those who are in final year will understand this better, the equivalent length. That you can calculate it using your arithmetic that you were taught by our own Dr. Afute, and you are going to get the same thing or similar. So when you come to streams, you will see that now the Reynolds number have increased. That means the turbulence is increasing. And you can relate the turbulence increasing because now the pressure of the water has been increased by the pump. And you will see that turbulence will increase. So you can see at first it was 6333. Now after this one, you are seeing that it's 63, and the final one is 63562. That's increased. And we have the balance. So now we come to the V4. Then when you come to the V4, right click, go to results, and you can see, okay, this one too, the index was not shown. The index was not shown because I didn't check it in. So just as I did for the first one, I'll go to the main flow sheet, double click on it, go to calculation options, and check the index in. Check the index and run. Run. Okay. Right. So when I run it, I can go to V4, and you see that V4 results, and you see that now the cavitation index for V4 is 0.027. So there is no, it's not liable to there's no avenue for cavitation to occur. It's not possible that it will occur within this. Wow. So people, this is where we will bring today's tutorial to fluid handling equipment. We have been able to use pipes, we have been able to use tanks, we have been able to use a valve and a pump. So you can explore the assignment. I'll post it on the page today. That will relate with maybe a compressor, and the compressor will be the same thing. The discharge pressure that you will need, it will be the same thing as you do. Do you have a question?
Um,
Okay, the
I just
nominal
wanted
size
to.
pipe diameter. Okay, so the nominal size pipe diameter is 2.5 inches. It's 2.5 inches, and it was calculated from here. It was calculated from here. We found the volumetric flow rate from the mass flow rate. Mass flow rate, density of water, 1,000 kilogram per meter cube. You manipulate it to get your flow rate, 10 meter cube. Then you convert the meter cube to feet cube per second. Then you put it there as well. Then you can see the density, because this is in feet cube. It's also going to be, it's not going to be kilogram, it's going to be pound. So you change the 1,000 kilogram per meter cube to pound per feet cube. Then you put it there into the pipe diameter, optimum diameter equation, then to get the to be 2.3. 2.3. So final years, I think this is a class for you. You are going to specify your pipes. And you can use this formula to specify your pipes. All right. Please, any question? All right. Okay. Chimesi, I've answered you 2.5.